Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about the periodic table. Alright, and when we talk about the periodic table, there is a lot to be said about how it is organized, why it is set up the way it is, and there is a lot more to this table than that meets the eye. Because when we first look at this table, what we see is letters, we see some numbers, and we've learned what these numbers and symbols mean, right? If we look at, for example, carbon, we know that its atomic number is 6, and we also know that its mass, its average mass, is 12.01 based on its isotopes, which we've talked about in the last chapter. Okay. Now, why is carbon, though, placed right here? And why is nitrogen here and oxygen, right? Well, you can see that they're going in increasing order, but for some reason at 10, the pattern repeats and jumps over to the other side of the table. Why is that? Okay. Well, today we're going to be talking about that, all right? And the periodic table was actually built as a predictive model, all right? Now let me show you this, all right? So here's a timeline of the development of the periodic table. Obviously, there was a lot of information that these scientists knew at their time. And they were trying to come up with ways to describe and organize how would we arrange elements in an orderly way and in a predictive manner. And Mendeleev, okay, what he did is he made predictions about 3 or 4 elements. And for example, you see here that there's a question mark on each of these boxes. That's because when Mendeleev was creating this table, he did not know what those elements were, but he knew that they existed and that one day they would be discovered and that they would have a very specific properties to them based on their location in the table, because he recognized that these elements shared characteristics and that as we work our way over, these characteristics match here. And he knew that, for example, number 68 would have characteristics that were similar to boron and aluminum, but he knew that they didn't exist because when they were counting the elements and working with them, according to their mass, you see how their masses increase over here from 65, 68, 72, 75. He knew that there's a space that was missing and that there would be elements that would be discovered, and he knew their properties based on where they're located on the table. And 68 eventually was found and discovered to be gallium, and 44 was scandium, and I think 72 was germanium. Yes, it was germanium. So these 3 elements were discovered after he died, and they basically proved that Mendeleev was correct, and he was kind of prophetic in the way that he knew that these elements existed and we didn't actually have the technology at the time to discover them. Okay, that's what made Mendeleev so great. All right, it wasn't that he just arranged a periodic table of elements based on properties and where they're located. It was that he actually used his table to predict future elements. Right, that's what made him so great. That's why people give him so much credit. Okay. Now, let's flip over and let's start talking about the modern periodic table that we know today. Okay, because back then it was very primitive. They did not have the technology to, I would say, isolate certain atoms. So it took a long time for us to get to the point where we were able to recognize and understand properties of certain elements. All right, so here's some vocabulary I want you to write down. I want you to write down a period, periodic law, and group. I want you to write down these definitions. So pause the video, write them down, and then we'll keep going, okay? Okay. All right, so down here we have a picture of the periodic table. Now this may look a little different than the one I've given in class or the ones you'll see in textbooks, all right? And that's because we take this inner transition group, see this bottom table, part of the block of the table, it would fit right in here. But because it's so long, it's hard to fit it all into one page. So typically they will take this inner transition metal group and move it down. We don't work with the inner transition metals very often. The only time we'll really dive into this section is when we talk about nuclear fission, which will be near the end of the year. Okay. So this is how the table is arranged. And now if we look here, we can see that there's this trend that comes. We go 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it repeats. Okay. We call this the periodic law. Okay. Every row is considered a period. You should have written this in your notes, okay? is a horizontal row. So this is period 1 through 7. All right, and as you work your way across, the characteristics change. Okay, so a pattern arises which states that when elements are arranged in order of increasing atomic number, there's a periodic repetition. So at every time it hits the end, the pattern repeats. So element 3, 11, 19, all are very similar. Okay, there's an arrangement that's happening. We're starting to see that there's this trend that's forming as we bounce as we hit this end to over here. Okay, because 11 is more like 3 than it would be out here, because there's no line for that. Okay. All right, now groups are our columns. Okay, we also call them families. So this is family 1, 2, and then we're actually going to skip the transition metals and the intertransition metals, and we will have group family 3, 4, 5, 6, 7. You see how these A's are right here? Okay, we'll get to, and I'll describe why we separate the A's and the B's. Okay, but for right now, I just want you to kind of ignore the intertransition and transition metals. Okay, so we have group 1 through 8. Those are the ones that I want you to know. And you'll see on your periodic table, I've labeled them. Do you see how they're in Roman numerals above? All right. So when I say family or group 2, I'm talking about this group here. And when I say group 3, I'm talking about this group, not this group. There's no numbers here. Okay. In some of these more detailed periodic tables, you'll see them labeled as B. But just know that when I'm saying them, I'm talking about this S and P blocks. Okay? All right. So that's all I need you to know about from this page, is that periods run horizontally and groups run vertically. All right? And groups are what share physical and chemical properties. All right? All right, now we can further divide this table into metals, nonmetals, and metalloids. You'll see that on my periodic table I have this kind of grayed out area. Now you're about to understand why it's grayed out. Okay? These are called metalloids, and I will go in depth in a minute about this. Okay? So first I want you to write down some of these definitions for metal, nonmetals, and metalloids. Okay, and I'm going to go through these. Okay, so if you need to pause it, go ahead and pause the video. All right. So a metal is a type of element that is a good conductor of heat and electric current. Freshly cut metals are reflective light, causing them to be shiny. Most metals are malleable, meaning they can be shaped into different physical forms, like thin sheets. Many metals are ductile, meaning they can be drawn and stretched into wires. The metal that I typically think of when I think of ductile, it's like the wires that are in your house. And that's like copper. Okay, copper wire is used in your house because it's a good conductor. It's malleable. You can bend it and shape it. And so can all the rest of these metals. Okay, the metals are this kind of orange color. All right. Now I'm going to jump to the nonmetals, the green side here, the light green. So a nonmetal is an element that tends to be a poor conductor of heat and electricity. All right, so it's the opposite of a metal. Nonmetals tend to have properties opposite of metals. So one exception is carbon, as graphite. So carbon is kind of a special one. It will have different properties that will go against the trends, but for the most part, it's only when they're in a specific structure or lattice. Okay. All right. So nonmetals basically are brittle. They're not malleable, right? And they can be shattered. They can't be put into wires. Okay. If you think about sulfur, we'll work with sulfur from time to time in the lab, and sulfur is like a powder, right? It's not like something you could form into it and shape. All right. And we'll talk about those characteristics of why they do what they do. Or why they behave like they do in chapter 3 when we get into chemical bonding, and we'll discuss why is it that metals have this characteristic. All right, in metalloids, this dark green section, or in my periodic table, this kind of dark section, it kind of separates my metals and my nonmetals. Right? They share characteristics of both. All right, but they tend to share more characteristics with nonmetals. Okay. They tend to be solid, do not exhibit luster, and are poor conductors of heat and electricity. Metalloids' behavior can be changed by using mixtures. For example, pure silicon is a poor conductor of electricity. All right, silicon is here. You may have heard of a place called Silicon Valley, right? That's where semiconductors are made in California, all right, or where they're developed. And silicon can actually be combined and form an alloy with other elements to become a great conductor. And that's why they're used in computer chips. All right. All right, so please make sure you're familiar with this page between metals, nonmetals, and then metalloids. All right, and be familiar with their characteristics. And keep in mind that as you work your way toward the metalloid section, they become more and more like nonmetals. And as you work your way toward this section, they become more like metals. So there's kind of like this gray area, but the properties at this end of the table are more metallic than I would say something that's closer to this metalloid section, right? So the trend for metals, it gets more metallic if you go this way, and they become more like nonmetals as you work this way. So there are kind of trends based on where they're located on how metal-like are they or how non-metal-like they are, okay? And this kind of gray area is in between. All right, let's go to this looks like our last page. And I've hinted at this and I've talked about it, but the main group elements are groups S, the blocks S and P. So if you can pause the video, I want you to write this down. Okay, it's groups 1, 2, and it says 13 through 18, but on my periodic table, I've labeled it as 1 through 8. So 3, 4, all the way to 8. Here they have it as 13 to 18. That's because they're using this table down here, and they're including the transition metals. So keep in mind, periodic tables will be different, right? They'll be labeled differently. Mine is more simply designed, all right? And I didn't really talk a lot about the inner transition metals, the transition metals, because we don't deal with them very much in this class, okay? All right. So when we look through here, I need you to be familiar with these terms, okay? So the alkali metals, alkali earth metals, halogens, and noble gases, all right? These are special group names. So if they belong in the first column, they're alkali metals, okay? They are very reactive. The alkaline earth metals are a little bit less reactive, and they are in the second column, okay? And we'll talk about why they're reactive, all right, and the type of way they are reacting to other things in Chapter 3. And then on the very end, we have our noble gases in purple. Okay, they're inert gases. They don't like to interact with anything, and we'll talk more about why that is. And then this pink column are the halogens, okay? And they are very reactive, okay? And we'll talk more about why that is, okay? Groups 3, 4, 5, 6, okay, they have names, but we're not going to learn them. So we just say group 3, group 4, group 5, group 6. Or you could say family 3, 4, 5, and 6. Right? Group and family are the same thing. So remember, main group elements are S and the P blocks. We're not talking about main group elements as transition metals or the inner transition metals, okay? And families and groups run vertically and periods run horizontally, all right? And the periodic law is basically the idea that when you hit the end, the pattern repeats, and the pattern repeats. That's the periodic law, all right? And please be able to distinguish between metals and nonmetals, and they're in the mixture of those, kind of like the shared characteristics of metalloids. All right? Okay, thanks for watching. If you have any questions, please come talk with me. This is a good overview of this section of the thing. Thanks. Bye.